Okay, let's move on. In the last lecture, we will talk about what is regression and linear regression and what is the cost function and how can we define the cost function and intuitions of cost function. Okay, so in the previous example, we just considered the simplified version of the cost function. That means that we just consider the one single variable of the parameters of this loss function, this mapping function. But in this lecture, let's think about more general, more difficult, more challenging version of the cost function. Let's say we have the two variable that define the this linear loss function, something like this. And in this case, the cost function can be represented like this as usual. And the goal of this linear regression problem is to find the parameter w that minimizes this loss function. Okay, so this is what I want to do. Okay, so let's see the detail. Okay, we have that. What is that? What is that? This is the model or mapping function or hypothesis. Okay. And we have the loss functions here. Okay. Actually, it's not a W1. It should be W is equal to W0, W1, because we consider in this example we consider the two variable. So the mapping function means the for fixed the W parameter W, this is a function of X, and the loss function means this is a function of the parameter W, something like this. Okay, so in this case we consider the more challenging scenario. Like this x-axis means the size of the pit, so it will be our input data. And let's think about the price of the house. It will be our output data set. So this each point means the training pair, like the x1 equals x1 is comma y1, x2 comma y2, something like this. So what I want to do? What I want to do is to find this straight line can be represented by W0 plus W1 times yeah, just X. Okay. So we want that this is the approximate version of the real Y. Okay. So here's an example. If the W0 is equal to 50, W1 is equal to 0.06, then our mapping function would be like this. 50 plus 0.06 times x, something like this. Then, if you remember the previous example, first of all, we should draw some cost function in the according to the variable or parameter w. So in the previous slide, we just consider W0, and we can draw this like the bowl shape the cost function. Then in this case, we have the two variable, right? Then how can we visualize this? How can we visualize this cost function? Okay, so actually to visualize this cost function with respect to the W0 and W1, it should be looks like this. This is W1 and W0, W1, and it should be loss of W, and it can be represented like this specifically, right? So with the two variable, we can define the loss function on the three-dimensional space, something like this. Then it can be looks like this. Yeah, this is the cost function of our problem with respect to the two variable W1 and no, it's not a W1, W0 and W1. Okay, so we're in W1, and this is the loss function of W0 and W1, like this. In this case, if we just to choose the one single variable here, let's say W is equal to W0, W1, okay, something like this. In this case, each, what is that? Negative 15 and plus 2, something like this, right? So in this case, the loss function, I mean the values of loss function of the negative 15 comma 2, it should be some values here. Okay, so this is just one example. Then with a number of possible combination of the W0 and W1, we can pick the point on here. Then finally we can draw some kinds of surface like this. Okay. In this case, the reddish color means it has the higher value than the blue colors values like this. Okay, so this is the three-dimensional representation of the cost function. Okay, so actually this cost function, this cost visualization is a similar shape with this function, but actually it is really hard to draw this 3D surface every time. So from now on, we want to use the more simplified version of this cost visualization. So from now on, we will use the contour plot or contour figure. What does that mean? Instead of using this 3D representation, we can represent this 3D representation like this. Okay, so you can see they have some ellipsoid, the circle like this, and they have the different color, right? And then these different colors it has a similar meaning in the 3D space. It means that these red colors means it has the large loss and loss functions, and the blue color means the small loss function, small loss values. Let's say the values, small loss values, right? One more thing is that the same color means they have the same loss values. It means that, let's say there are 3 points here. They have the same color. It means that the L, W, they have the same same loss values, so it means that these three values have the same LW. Okay, so what do you want to do? What do you want to do? What is the goal of this minimization problem? We want to find, it was error W, right? So we want to find the W that minimizes this loss function, right? So in this, as you can see here, we want to find some point that represent the minimum values among the whole other values. Okay, so here's the example. If we just pick this point, it looks like the set each is the W0, W1. Let's just think about the W0 is equal to theta 0 anyway. So if W0 is equal to 800, and then the W1 is equal to negative 0.15, then the mapping function with these two variables looks like this. Why? Because we can represent this mapping function then like the W0 plus W1 times X, something like this. And if the W0 is equal to 800 and W1 is equal to negative, okay, where is that? Yeah, negative 0.15. Oh no, sorry about that. It should be looks like this. Okay, so this is the mapping function. Then what is value mean here? What is value mean here? This value means we can compute the distance between the estimated values with the real values here, like the distance. This is error, right? So like this, we can compute the every errors at each point and then just aggregate these errors. That it means that this loss function represents this value. Okay, so as you can see, the errors are really large. So we just guess this loss this mapping function is not a good indicator that approximate this data set. Okay, then let's think about another mapping function. We just think about this, but in this here we can think about another point here. Then in this case, the W1 is equal to 350 and W1 is equal to 0, something like this. And in this case, this mapping function looks like this, because we already know the just 350 plus 6 times x is just equal to 360. So 350. So this is just like this. Okay. So in this case, we can also measure the distance between real and estimated value, something like this. Compared to this example, this looks like they have the much smaller errors than this one. So that's why this point have the more flourish the value. So we can say that this point is more much closer to the solution than this point, right? but still there are some errors here. So let's think about more proper point like this. What about this? What about this point? Okay, this point also have some values here, so it can be mapped to the lines are here. So we can also measure the distance between real values and estimated values. So we can compute some cost function or loss function. Loss values are here. Then this is another example here. There we also have some W0 and W1 values, and we can plot the straight line with respect to these two values like this. Okay, so as you can see here, we can also measure the distance for every pairs, every samples in the training data set. But I think that these values are much smaller than this one, right? So it means that we could say that these values, this parameter, will be the closer to the real ground truth. So we could say that this W0 and W1 are well approximating our training data set. So we could say these values will be the approximated version of the ground truth. Okay, so this is the intuition of the cost function. So actually, to define the cost function, we can use several kinds of loss functions. Okay, let's go back to the first slide. Okay, so in this case, we just think about this distance term as a scared absolute value, something like this. But what about this? We could use the other distance term, something like this. So depending on how we could define this distance, we can say that we use the which cost function. Okay, so let's say that there is two very well-known cost function. The first one is the mean squared error or mean squared error loss function. So actually, the MSE is one of the most popular cost function that is defined like that. This is what we discussed so far. Another example is the mean absolute error, or called the MAE. So MAE is defined looks like this. The main difference of the mean squared errors and the mean absolute errors are here. Okay. In the MSE, they measure the squared of the difference, but in MAE, they just measure the absolute values. Okay. So okay, let's think like that. Okay. So do you remember the two desired property of the cost function? Where's that? Yeah, here. What was that? The first one is the cost function should be symmetric around 0 or around 0, right? And the second one is the cost function should penalize a large mistake and very large mistake similarly, like this. So these examples, cost function examples, that cost function satisfy those two desirable property. Okay, let's think about that. When we define the cost function, there is a trade-off. between the statistical and computational property. What does that mean? So I could say like this: if we want to better statistical property, it means that, let's say, we want to make our network to be robust to the outlier. It is related to the second desirable property. We have to give up the good computational property. What does that mean? Okay, let's see this figure. Okay, so the x-axis means the residual or errors of the estimated values with the real values, means like f w x n negative minus y n, right? So this is residual. Okay, when we just think about MSE, okay, we use this color. MSE looks like this, because it has the skeleton. It looks like the ball shape like this. And when we think about the MAE, mean absolute error. Oh, there is some mistake. Okay, this error, it should be looks like this. This is MAE. Okay. So as you can see here, MSE and MAE have that satisfy the first desirable property. What was that? Symmetry, right? Because they are symmetry across the f value 0, but when you think about the second property, that represent the robustness to outlier. Actually, okay, let's think about that. If we just think about this residual and this residual and this residual, the loss values of MSE each looks like this, maybe somewhere, right? So as increasing the errors to this MSE MSE cost function, MSE cost functions is getting bigger and bigger. So it means that, let's think about some examples. Like if we have some training samples like this, and if there is some outliers here, we want to find the straight line, something like this. But if we just use the MSE or MAE, maybe they looks like this. They can generate the mapping function looks like this. So we want to find like this. Okay. So then, how can we do that? If we just to reduce the effect of the very large residual, let's say, looks like this. We can consider these samples and these samples similarly, because the distance, oh, it's not distance, because the distance, let's say this is E1, this is E2. So if there is E1 here, E2 here, but if we use this loss function, the loss values are same, even though they have the very different error or residue. So if we use this kind of loss function, we can find the mapping function looks like this more properly rather than this one. Okay, so this is called the lowest cost function. Then what is the equation of this loss cost function? Actually, it is also called there are several kinds of lowest cost function, but there are very two well-known methods like the Huber norm or Huber distance or Huber cost function or Turkey loss function or Turkey cost function. Then if we have the cost function something like this, then we can have the property looks like this. So that's what we want to do. But I will give you some homework. Actually, you don't have to submit, but please find what is this equation. But comparing to these two well-known loss functions like the MSE or MAE, these loss functions have the much complicating form or more complex the equation. So it means that it required more computational complexity than the MSC or MAE. So we could say there is some trade-off between the statistical property and computational property. So to wrap, so if you want to develop your good loss function or good cost function, there might be some trade-off. If there's no trade-off, it will be nice, right? But most cost functions have the trade-off, so you have to think about what is your role and why do you want to develop this loss functions or cost function. Okay, so please remember this page. Here are another here's another example. No, it's not an example, it's just a recommendation. Actually, I'm not sure how much of you heard about the CBPR. The CBPR is the most prominent and the most biggest conference in computer vision field. So in the last year, there was a very interesting paper that is called the general and adaptive robust loss function in Google. So here is the idea. So actually, this is the visualization of the previous cost functions, but in this paper, they generalized the whole of the previous the loss functions with some variable alpha and x. Okay, so actually this paper is really nice and really intuitive, but it might be hard to understand. So I would say you can take a time to understand this paper, then it will be helpful for your further research or further your project. Okay, I strongly suggest you to read this paper. Okay, so this is the related to cost function things. Okay, where are we now? Okay, we have some function or some cost function, right? How can we define that? Like some variable with the summation of some cost function between our estimated values with the real values from n is equal to 1 to the number of the data, like this. Now we have the proper cost function, and we have the training data set. And then what do we want to do? What do we want to do? We want to find these values that minimize this loss function, right? How can you do that? How can you do that? Actually, we already do that, right? As you can see here, for the loss function, we try to find the minimum values by just to randomly choose the some values like this, right? Then we found that this point is the minimum of this loss function, right? Actually, this procedure is called the grid search. What does that mean? The grid search is one of the simplest optimization algorithm. We compute the cost over whole values W in a grid and pick the best. Actually, this is a very brute force, but it's extremely simple, right? It's extremely simple, right? We can just try the possibility of the W. Let's say we can try the many W, and then just pick. Okay, this parameters is makes the minimum loss functions here. Then we can choose this one, and this is our parameter that learn the own training data set, right? But as you can see here, as you can easily think that there are too many for loop. Do you know what it means, right? Because most of you are from the computer science field, so you can implement some code for your project. And if you want to implement this part using the grid search, you need a for loop, right? Something like this. Within this for loop, you have to compute the loss function for every possible W, right? So it will generate the exponential computational complexity, right? We don't want this, right? Because we want to make our algorithms more efficient and effective, right? So we need a more fancy method or smarter method. So here's some more smarter method. Okay. How about using the gradient, right? So, oh wait, do you know the gradient? What does it mean? If you don't know the gradient, please search or find what this gradient mean. So here we can just say that the gradient is the slope of the tangent to the function. What does that mean? Let's draw some contour figure like this, I'm not sure, like this, right? Okay, let's think about this. This is the parameter or point of the W1, W0 and W1, something like this. And these colors means the values of this loss function, like this, right? When you think about this in a 3D surface, it should be, how can I draw this? Looks like this. It's just some surface, and we are here, right? we want to find the minimum values, then it means that we have to go to the minimum values. It means that we have to downhill from this value to the more lower value, right? Then how can you do that? First of all, we have to define the direction of the our further step. So if we are here, let's think about this is kind of the mountain, something like this. If we are here, we can find the 360-degree. We can think about the every direction like this, and then we can choose the which direction is the most efficient way to down the mountain, right? So as you can see here, we could say that this direction is the optimal direction that we want to go, right? So in this case, this direction is called the gradient. Okay, gradient, right? So the gradient means the slope of the tangent to the function. So it points to the directions of the largest increase of the function. Okay, so this is the meaning of the gradient. So I think already most of you already learned about this. This is the related to the in Korea 미적분. So you can find the largest increase of the function with the gradient, right? So the idea of the gradient descent is just to use the gradient. So it means that we can start with some parameter called the W0 and W1. Let's say we could start the W0 equals 1 and W1 is equal to 0. And we want to keep changing the W0 and W1 to reduce our loss function, because we have to find the minimum value until we hopefully end up at the minimum. Okay, this is the intuition of the algorithms of the gradient descent. Okay, what is that? Let's see the example here. We have a two variable W0 and W1, okay? And we have a loss function here. Let's say W0 and W1 here in the three-dimensional space, something like this. We want to find the minimum value and minimum point. Looks like this, right? How can we do this? If we use the grid search algorithm, we have to measure the cost function at every point here, but it's not efficient. It is very fruitful, but it's not efficient. Then what we want to do, we can just start from the random initial parameter. Let's say W0 1 W1 this one means let's say the 0. The 0 means the initial state of our parameter. Okay, what do you want to do? We could downhill this mountain by following the gradient like this, and then after we also in here we want to go like this, because when comparing the every direction, it's not optimal. I think this is more optimal like this. And when we here, we can also find another direction like this. After some iteration, we can just find our minimum values are here. This is the general idea of the gradient descent. Okay. Let's say this is the gradient descent. Gradient descent. What if we start from the different initial state or if different initial point? Let's say this is the previous initial value. What if we start from these initial values? Let's say W0 initial values. In this case, we can follow the another procedure. Let's say if we are here, we can find the optimal direction looks like this, and if we are here, we can find the optimal looks like this, this. Finally, we are alive here, right? Comparing to this, when we use the different initial values, we can find another optimal point here. So when we comparing to this and this, we could say that this is much smaller values than this one. So we could say this initial value some more good starting point than this one. So it means that what this mean? What this means? We have to choose the more proper initial values to make our gradient descent algorithm to be converted as on more optimal values. Okay, so I would say the initial values or initial parameters are more important than the other point. Okay, so this is the general idea of gradient descent. Okay, so let's formalize what is gradient descent is. So this is the gradient descent algorithm. So as you can see here, gradient descent is the iteration algorithm until convergence. So we can use some kinds of the for loop or while loop, something like this. If you don't have any idea about this, please find what it means. So it is very important. Anyway, so this is the algorithmic description of the gradient descent. Okay, so we have two variables. Let's say W0 and W1. The goal of our gradient descent algorithm is this parameter W that minimize our loss functions. Loss function looks like this. Okay. So if you remember the gradient, if we remember we want to use the gradient, let's say we can start from some initial values here, and we want to follow this gradient from at the current point. This is the gradient of the L W0 is and W1 at the current point W0 and W1. Okay. This is the gradient, and okay, let's do that. And there is some constant value, so this is called the running rate. So what does that mean? We want to move these values to this gradient with the amount of this running rate. Okay, so depending on this learning rate, we can adjust the speed of the convergence of our algorithm. So let's think about it like this. Okay, if we have the learning rate, let's say the 0.1, and it looks like this. But if we have the, let's say we have the 0.01, something like this, it is move very much slower, like this, much slower, something like this. Or if we have the another learning rate, let's say just 1, it could move something like this, right? As you can see here, often depending on this learning rate, the shape or the path of the gradient descent algorithm will be changed, right? So it means that the learning rate is also very important factors in the gradient descent algorithm. So okay, so this is the learning rate. Okay, with this equation, we can update this parameter W0 as the next parameter values, right? And then with the we have the W0 and we also have the W1, right? So for W1, we want to do the similar things on with this equation. We from the initial W1, we want to compute the gradient of the loss function and compute the values with this learning rate, and we can find the next W1 like this. So by evolving the iteration of this whole procedure, we can finally get the optimal W. It's not optimal. It's suboptimal W values of this loss function. Okay, so this is the general rules of the gradient descent algorithms. Okay. Okay, so let's see some more details in the gradient descent algorithm. This is just one step of the gradient descent algorithm. Okay, let's say we have the loss function looks like this, and we looks like this, and we start from the initial values at arbitrary point here, like this. So what we want to do is we have to compute the gradient at this point, right? To compute this equation, to compute this value, right? So what is gradient at this point? What is gradient of this point? It is the tangent line of this graph, right? If you don't understand why this gradient looks like this, please find some other material what this gradient means. Okay. Anyway, so in this case, gradient looks like this. Okay. So in this case, so the gradient of the sign of the gradient of these values, this loss function should be what? Should be positive values, right? Positive values because the slope looks like this, right? So in this case, the parameter W1 minus some learning rate with parameter values means we decrease the parameter W1 looks like this, right? It means that we just follow the lines like here, until convergence, okay? So it means that if the gradient of the loss function is positive, we should decrease our variable, right? What about another case? If we start here, the gradient at this point should be like this. So in this case, this is the negative slope, right? This is a positive slope. Okay. So in this case, this form. Okay. Let's write. Okay. The gradient of this loss function should be negative, right? Negative, right? So in this case, this value will be what? Positive, right? So in this case, this parameter should be increased, right? So it means that the values of our learning algorithm is depending on the sign of gradient and the values of gradient. Okay, so one more things are here. What if we start from here? Okay. If we think that this is initial state, then we can rewrite the general rule like this, something like this, right? In this case, what is the tangent line at this point? It should be like this. Okay? Then, what is that? In this case, it should be what? 0, right? So we don't have any values here, so it means that the rule of the gradient descent algorithm is just like the W1 should be W1. What does that mean? We cannot update this parameter W1 if we just start from this initial state. So it means that we just find the solution without any algorithm, right? So this is the good thing, right? But is it really a good thing? Because let's think about another examples here. Let's say we have the loss function, more general loss function looks like this. Okay. Loss function looks like this. If we just start from here, but your optimal values are here, right? Then if we just use the gradient descent algorithm and we just start from here, we don't have any way to go uphill and downhill here. So this is the limitation of the gradient descent. Okay. So to solve this problem, there are so many variant of the gradient descent. But in today's lecture, we just think about the original gradient descent. Okay, so this is the gradient descent. Okay, one more thing. Let's rethink about the one steps of gradient descent, something like this, right? We start from the some variable w1, and we update this w1 with the gradient with the learning rate, right? So we just call this is the learning rate, right? So let's think about like this. If we have the slope, if we have the loss function looks like this, and we start from here. This is the loss functions. Start from here, and what if the alpha, the learning rate, is too small? We have to follow the lines very slowly, right? Because the learning rates determine the magnitude of our step, right? So in this case, it will be the very slow. So it means that we need a more computational complexity than the another choice of the lambda, right? What about the lambda? Let's say this is just alpha, right? What if the alpha is too large? What if alpha is too large? And we start from here. In this case, okay, let's think like that. If we just start from here. If the learning rate is too large, we want to find the global solution looks like this, but if the learning rate is too large, the next step will be looks like this. Why? Because the tangent lines are here, so we should move this point to this direction, but we should multiply the large values, so the next point looks like this. So in this case, the gradient descent can overshoot the minimum, and in the another step, it looks like this, and looks like this, and looks like this. So in this case, the gradient descent algorithms may fail to converge or even diverge, right? So that's why we should carefully choose our learning rate when solving the gradient descent algorithm. Okay, so this is the end of today's lecture. Today we have learned what is regression and what is linear regression, and how can we formulate this and how to solve this. And in the next lecture, we will learn what is the classification and logistic regression, and what is the difference between the linear regression